Hello and welcome back to the Energy Systems and Management course. I'm excited to have you join me as we explore electricity systems. Whether you're a seasoned expert or new to this subject, I promise you'll gain valuable insights from our discussion. So let's dive right in. The key learning outcomes for this lecture are that we hope you'll be able to describe and analyze established electricity grid systems and see what changes are on the horizon in the future. As we change how we use and generate our energy, we'll also be looking at developments in generation, transmission and distribution. These three form the core of the energy grid network. Electricity needs to be created in generation, transmitted over long distances, and then delivered to the consumer in local distribution. So electricity, as you might know, is not counted as a primary energy source or fuel, like coal or biomass. You can't go mining for electricity or dig it up for consumption. With the exception of lightning and other forms of static electricity, it doesn't really exist in nature. It has to be made or generated. Although, if you were to make some kind of lightning-powered energy plant, that could actually be a game changer. Sticking to reality, electricity is only a means by which energy is distributed and used. It is an energy carrier, and therefore it is an energy vector. Once the electricity is generated and delivered to the consumer, it is in a form that is versatile, easily converted into other forms of energy. So heat, light and motion are all fairly easily accessible, and it does this pretty effectively, and can be very efficient at the point of use, or the point of load. One example would be an electric bar heater. Now, depending on how you set the boundaries of your efficiency measurement, these can be described as being nearly 100% efficient, far beyond the efficiency limits for direct utilizations of fuels in heat engines. Also at the point of use, except in certain conditions, like photocopiers, there's no environmental impact from the electricity use. All the polluting behavior that generated the electricity is far away in distant power stations and in a centralized point, where it can potentially be dealt with. Another benefit is compactness. Energy can be delivered through relatively small wires and cables, to what are proportionately very small motors. An electric motor with a similar horsepower to the petrol motor is significantly smaller. This can be much more convenient and controllable than the equivalent mechanical system, even over relatively short distances. So if you have an operation which needs transmission of energy, even over a few meters, it may be more cost-effective to transfer that energy into electricity and deliver it to the target, and then transfer it back into whatever other form it was needed. Obviously, there is efficiency hit every time you do this transmission and change of energy form, but it can work out to the advantage depending on the necessities of the particular case study. There are, however, disadvantages with electrical systems, and the biggest disadvantage is storage. While there are methods that can store electricity, there are limits on the storage density and how long the energy can be stored. And in most cases, we're looking to store the energy for a long period of time, many months. So we might want to take the abundant solar energy in the summer and supply it for heat in the winter. For example, batteries have a finite lifespan and can only be recharged a fixed number of times before needing replacement. At the utility scale, at the kind of scale where we're talking about powering industries or homes, this really adds up. There are also the high capital costs for setting them up, and the costs also in both raw resources and financial upkeep. So electricity has to be effectively distributed from generators to consumers. There's no other place for it to go. To be fair, historically, this was not that much of a challenge, as the first drops of electricity were typically either small communities or rich estates, which didn't have to consider long-distance transmission or grid stability. You would have a small collection of buildings connected to a single generator. But if you fast forward to now, we have these large internationally connected economies that see huge swings in demand for their energy across a single day, let alone a month or two. We have a wide array of potential energy sources, baseload, intermissive and thermal, and extensive network required to get the energy where it is needed. And our economy relies on these established electricity systems. Here's the image showing an established electricity system. This is the general framework of the current power supply grid. We have these three pillars of any electrical system: generation, transmission and distribution. And we'll go through these on the image on the left. So on the image, on the top left, we have our power station. Generating electricity is a pretty high voltage, 23 kilovolts, which is a balance between the practicalities of the power station generators in terms of the coils around the magnets, and in terms of the materials that are used for cabling, and their tolerances of both high current and high voltage. This is then taken to a transformer, which will be immediately adjacent to the power plant, and transformed into very high voltage. So 400 kilovolts, that is 400,000 volts, with a relatively low current for long-distance transmission. Now, the reason for this is simple. The more current you have flowing through a cable, the more energy is going to be lost as heat from the resistance in the cable. If I compare electric cables with water pipes, the cable resistance is like the sand in the water pipe. It causes the equivalent of friction, which in the context of electricity and friction in general is heat. If the power was to be pushed directly down the wires from the power plant at the 22 kilovolts, but high current, they'd get very hot and could even fail. By increasing the voltage, we reduce the current and reduce the temperature, and this maintains the total energy going through the system. Nevertheless, around 5% of the electricity generated from generators is lost in long-distance transportation in large countries like the US, with slightly less lost in smaller countries like the UK. Simply because it's got less far to go, the voltage could be raised even higher to reduce these losses further. So these losses are a set balance. The fact that 400 kilovolts is chosen as a compromise, but if you went higher under 400 would be the risk of arcing. This is like artificial lightning. Super high voltage electricity could exceed the resistance of the air and cause a shorting of the system between the cables, or between the cables in the ground, or say, a nearby tree. So this is why the electricity cables over land are typically suspended high above the ground, and above any possible shorting point once we get to the local distribution. So once we're getting closer to the consumer, the transformers reduce the voltage back down at substations or similar, thereby increasing the current. A three-phase supply typically runs at 450 volts. And actually, you can use this directly. You can see this around and about. It's a slightly different sort of plug, usually large and grey, circular, about the size of a 1-liter drinks bottle. You may even see them in some of the large buildings, or in industrial settings for normal consumption. However, the three phases are separated into 3 individual phases at 230 volts, with a typical maximum current at the plug of 13 amps. Although this is limited by the fuses in the plug socket, so higher currents can be drawn with suitable fuses. But typical household supplies are limited to 13 amps for safety reasons. So for a large apartment block, 3-phase electricity may enter into the building at the bottom of the building, where the main junction box is, and at that point, it can be split into a single phase for each group of 3 flats. So there'd be one set of flats with one of the phases, one set with another phase, and one set with the third phase. This way, the electricity reaches the consumer in a very usable voltage and current availability. It is important to mention that the increasing portion of renewable power in the grid mix has had the effect of destabilizing existing energy supply systems, making them unpredictable beyond the range of weather forecasts. This effectively has put limits on how much electricity can be generated from renewables within these existing energy frameworks. However, since decarbonization is necessary to achieve climate goals, we're going to have to find new ways to deal with increasing renewable capacity. This will require future smart control systems that will distribute the energy more effectively to where it is needed, and these will become increasingly important in future grid systems. Here are a few summarizing points we face in this period of massive change to both where and how we get our power, with environmental concerns primarily driving these changes, while the transmission systems are mainly retaining their existing roles. Both the distribution and generation parts of the electricity system are set to change rapidly. Additionally, new energy concepts and new energy uses, for example, electric vehicles, add their challenges and need to be considered in the future energy makeup of our societies. How many of these electric cars we will have and where we will charge them is a significant challenge for urban planning. Thank you for joining me in this short lecture video. I hope you found the content both informative and engaging. For a more in-depth understanding of the topics covered, please refer to your course handout, which accompanies this lecture video. The handout, prepared by Professor Zandi, contains valuable supplementary materials that will enrich your learning experience. Your commitment to education is greatly appreciated. If you have any questions or need further clarification, don't hesitate to reach out. We're here to support your academic journey. Once again, thank you for watching, and I look forward to our next learning opportunity together.